Hello, welcome everyone. In today's lecture, we are going to look at one of the two criteria that we use for predicting the yield of ductile materials. Again, to kind of reinforce what we learned last time, ductile materials are materials which basically have a failure strain of more than 5% in tension. Okay? So these include metals and alloys and so on, many of the materials that we use in engineering. Okay? And today we are going to look at one specific criteria, what is called as a Tresca criteria. Okay? So by the end of the lecture, what you will be able to do is calculate the safety factor for ductile materials using the Tresca criteria. Okay? So what is the Tresca criteria? The first thing you need to know is that it is used for yielding or predicting the yielding of ductile materials. Okay? And one difference between ductile materials and brittle materials is that the ductile materials have similar yield strength in both tension and compression. So what you learned last time is that when you look at a brittle material, the yield strength or the failure strength in compression is quite a bit larger than the failure strength in tension. But in ductile materials, the stress strain curve is very similar in both tension and compression. So essentially the yield strength is also quite similar. Okay? So what does this Tresca criteria imply? The Tresca criteria, and sometimes it's also called as the maximum shear stress criteria. Okay? So that's another phrase that people use often. This criteria essentially says that a ductile material will start to yield, that is undergo plastic deformation, when the maximum shear stress reaches a critical value. Okay? So again, I want you to understand this clearly. If you think of a body that is under some kind of a loading, okay? So each point under the body could be under a different stress state. Okay? For each of these points in the body, you can calculate what is the maximum shear stress at that point. Okay? If any of these points, okay, have a tau max that exceeds this critical value, then the material will start to yield from that point. Okay? So if you don't want the material to yield anywhere, then the tau max at any point within the material has to be less than this critical value. So what is this critical value? So if you recall, the maximum shear stress at a point, okay, is given by sigma 1 minus sigma 3 divided by 2, where sigma 1 is the principal stress number 1 and sigma 3 is the principal stress number 3, and you always order in such a way that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3. Okay? So tau max is sigma 1 minus sigma 3 divided by 2. The maximum shear stress criteria, the Tresca criteria, essentially says that when this tau max reaches Sy divided by 2, the material yields. So what is this Sy divided by 2, or what is this Sy? Sy is the yield strength in tension that you obtain from a uniaxial tension test. So if you recall a stress strain curve for a ductile material, so if this is sigma and say this is epsilon, then initially you have an elastic region, right? Then it becomes slightly nonlinear, then it starts to yield, and then it starts to strain harden, and then eventually neck and fail. Okay, so that is the stress strain curve. And typically the way you define the yield strength, Sy, right, is by doing this 0.2% offset method. Okay? Okay, this is something that you should have learned in your solid mechanics class. So this value here, the yield strength, is what this Sy is. Okay? So what this criteria essentially says is that if the maximum shear stress at a point reaches Sy for that particular material divided by 2, then the material will yield at that point. Okay? So again, I want to kind of give you the holistic view here. So how do you determine whether something is going to fail or not, or something is going to yield or not? Okay? Say suppose you make a structural material or structural part out of, say, stainless steel. Okay? Now you know the stress strain curve for the stainless steel, which means that you know Sy. Okay? Now say you make this bar of stainless steel and then you are subjected to bending or bending and torsion or whatever it is, right? So in that particular case, you can figure out, okay, this bar of stainless steel is essentially going to have a critical point somewhere in the material. Okay? At that critical point, where you have the maximum shear stress of the whole material, tau max, you find out whether at that critical point, this tau max is greater than Sy over 2. If it is not, then the stainless steel bar is not going to yield. On the other hand, if the tau max at that critical point is greater than Sy over 2, then yielding will start at that point, and it might propagate depending on how the loading is applied and so on. Okay? So that is how you have to kind of think about it. Another way of considering this is that tau max is sigma 1 minus sigma 3 divided by 2. And if tau max exceeds Sy over 2, then the material leads. Or the other way to put it is that sigma 1 minus sigma 3, if the difference actually equals Sy, that is when the material starts to yield. Okay? Now, if this tau max is less than Sy over 2, then it makes sense to define a factor of safety n. So the factor of safety n is nothing but Sy over 2 tau max. Okay, and the reason is that the criteria for yielding is nothing but tau max equal to Sy over 2. Okay, so n by definition is going to be Sy divided by 2 tau max. Okay, and that is what I have written here. Okay. Now, as long as tau max is less than Sy over 2, then n will be greater than 1, and that essentially means that you have a real factor of safety. On the other hand, if tau max exceeds Sy divided by 2, then the value of n will be less than 1, which means that the material or that particular part is actually going to yield, or in other words, it's going to fail. Okay, so that is what Tresca criteria means for ductile materials. Okay. Now again, we can represent this particular criteria in a graphical form, and just as we did for brittle materials, we look at the simplest case, which is the 2D stress state. So essentially, let's assume that sigma 1 and sigma 2 are the two principal stresses. Sigma 3, of course, is 0. In that particular case, the failure envelope for a brittle or ductile material based on Tresca criteria will essentially look like this hexagon. Okay, it is not a perfect hexagon, it looks like a hexagon. Okay, okay, and how do we get this hexagon shape? Okay, again, in this case, sigma 1 and sigma 2 are just parameters. Okay, the two principal stresses are just parameters, and essentially we are trying to plot the failure envelope based on the varying, based on how sigma 1 and sigma 2 varies. Okay. Now, let's try to understand why we get this particular shape. Okay. Let's just first look at region number 1 here. Okay. So, in region number 1, both sigma 1 and sigma 2 are greater than 0. Okay. And sigma 3, of course, is 0. Right. So, if you look at region 1, so let me just write this more clearly. So region 1, you have sigma 3 is equal to 0, okay, and sigma 1 and sigma 2 are both greater than or equal to 0. Okay, so in this case, tau max is going to be nothing but sigma 1 or 2 minus sigma 3 divided by 2, which is nothing but sigma 1 or sigma 2 divided by 2. Okay, again, in this case, I am not assuming that sigma 1 is always greater than sigma 2. Sigma 1 and sigma 2 are just the variables. Okay, so in that case, whichever is greater than, whichever is the higher value, if that value is going to be less than your Sy, then it's not going to fail. Okay. So another way to kind of think about it is that let's look at a specific point here. Okay, so let's say this point here. Okay, in that point, or actually let me choose a better point to illustrate this. So let's say you choose a point here. Okay, in that point, your sigma 2 is greater than sigma 1. Okay, so in this case, sigma 2 is the highest principal stress. Sigma 1 is the second principal stress, and sigma 3, of course, is 0, right? So in that case, your tau max is going to be sigma 2 minus 0, which is sigma 3 divided by 2. Okay? And as long as this is less than or equal to Sy over 2, then the material will not yield, which essentially means that if sigma 2 is less than Sy, then the material will not yield. If you choose a point somewhere here, the criteria that you will get is that if sigma 1 is less than Sy, then the material will not yield. Okay? So essentially, in this whole square here, okay, as long as sigma 1 and sigma 2 are both less than Sy, there will be no yielding. So as long as you're within that square, you don't have to worry about the material yielding. The moment you step out of that square, the material is going to yield. Okay? So that is how you get the square on the first quadrant. If you look at the third quadrant here, okay, it's a little different. It's a triangle, okay, rather than a square. Okay? And why is that a triangle? The reason is, if you look at region number 3, okay, your sigma 1 is negative and sigma 2 is positive. Okay, so sigma 2 is greater than 0 and sigma 3 or sigma 1 is less than 0. Okay, that is in quadrant 3. Okay. Actually, it's quadrant 2, sorry. It's quadrant 2, not quadrant 3. Okay, so in quadrant 2, you have sigma 1 less than 0 and sigma 2 greater than 0. Okay, now, in this case, your tau max is going to be, sorry, it's just a little bit messy here. So your tau max, wow, something is wrong here. So let me just use this part. Tau max is going to be sigma 2 minus sigma 1 divided by 2. Okay, so that is going to be your tau max. Okay, now sigma 1 is less than 0 and sigma 2 is greater than 0. So what does that actually mean? It means that you have less room for error. Okay, if sigma 2 is equal to Sy, the only value of sigma 1 that you can tolerate is actually 0. So this point here. This point here. Okay? So that is the only point you can tolerate. At that value of sigma 2, if sigma 1 becomes even slightly lower than 0, you're going to be here. And you're going to fail. Okay? Because this value will be greater than Sy over 2. Okay? Now, if you look at a point somewhere here, okay, sigma 2 is lower, and then sigma 1 is more negative now. Okay, so that sigma 2 minus sigma 1 is going to be still equal to Sy. Okay, so essentially, if you start from here, then as you try to increase sigma 1 in terms of magnitude, essentially as sigma 1 becomes more and more negative, then sigma 2 has to progressively come down. That is the only way you can make sure that the maximum shear stress does not exceed Sy over 2. Okay, and that is why essentially you have this kind of a slanted line here. Okay, so you can essentially use the same arguments to figure out that this line also has to be slanted. So whenever sigma 1 and sigma 2 are of different signs, you have less room for error. Okay? On the other hand, when sigma 1 and sigma 2 are both positive, or sigma 1 and sigma 2 are both negative, then you have more room for error. Okay? So essentially you have a square, and here you have a triangle, which has a smaller area, obviously, than the square. Okay? And the other thing that you notice here is that both in the positive direction and the negative direction, you essentially have the same Sy. Okay? Which was different for brittle materials. It was SUT in the tensile axis and SUC in the compressive axis. Here, both the compressive strength and the tensile strength are the same. Okay? So that is how you get this kind of a failure envelope for the Tresca criteria for a 2D case for a ductile material. Okay, again, what I mean by this failure envelope is that if you are within this hexagon-like area, you are not going to yield. Okay, and if you are outside that, the material is going to yield. Okay, so this is sometimes also called as the yield surface, okay, or the yield curve, depending on whether it's in 2 dimensions or 3 dimensions. You can, of course, extend this to the 3D case. Okay, of course, then the representation becomes a little bit more, harder to do, but it is something that you can visualize in a computer quite easily. Okay, but that's something that we will not be looking at in this particular class. If you go to a more advanced mechanics class, there you look at 3D yield surfaces based on both Tresca criteria and what is called as a von Mises criteria. Okay, I hope that this particular idea is clear. Okay, this is just a conceptual way of understanding what a Tresca criteria means using a graphical method. But the key idea is that if the maximum shear stress at a point exceeds SI/2, then that material will yield at that particular point. Okay, that is essentially the crux of Tresca criteria. Okay, I hope this was clear, and I'll see you in the next class. Thank you.